Oh, well, hey out there, all you crazy cats and kittens. This is Slagle from Big Cat Rescue. Just wanted to let you guys know that we're going to continue on with our learning today. We're going to be doing sampling distributions and confidence intervals for difference of means. So the notation is pretty simple. Let's go ahead and get a pretty color. The notation is pretty simple. You have two populations, one or two. We might call them something else in this scenario. The parameters for population 1 and 2 that we are estimating and using is the mean of the actual mean of the population 1 and the actual mean of the population 2. We are estimating the actual mean of population 1 with the sample mean from our sample. We are estimating the actual mean of population 2 with the sample mean from sample 2. And the sample sizes are N1 and N2. Isn't that special? My goodness. The question, I want to put everything in a context today. The question that we're going to be talking about is, are men really taller than women on average? Is this actually true? Of course, this is the most extreme case. This is the world's tallest man next to the world's shortest woman. This is from, I think, a New York Times article, but that dude's 8'1". That's insane. There are plenty of women that are taller than men. In fact, there are some funny couples you can find and stuff online where the lady towers over her husband or whatever in the red carpet shot. So it's pretty funny. But there are extremes in either end. But on average, is this really true? And so we're going to do an investigation with some sample data that we already collected earlier in the year. I don't know if you guys remember, you came in and we measured your height, we measured your wingspan, and your limbo fail height, and kind of put those together. All right, let's keep cruising. Before we move on, you need to remember that if you are taking two random variables and adding them together, and you're taking the mean of that, the mean of a sum of two variables is the sum of their means, which kind of is intuitive, and the mean of a difference is the difference of their means. And if they were sampled independently, then their variance, the variance of a sum, is the sum of the variances. Remember, variance is just the standard deviation squared. And the variance of a difference of two random variables is still a sum. So with variance, these stay positive. This stays positive either way, it doesn't matter. And then with the means, it follows whatever sign is present in the addition or subtraction of those random variables. And we've gone over that before, but it's nice to have a quick review. So let's take a look at this in terms of height. I'm going to do a quick review on sampling distributions because I think we could use it at this point. But basically, let's say this is the the height of all males, and this is the distribution of all males' heights, and it has a mean. So this is mu of x, or rather, let's say this. I'm going to call this rather mu of m. Let's go ahead and make it. Oh well, hello, Oscar. How can I help you? You sound distraught. What's happening in Kung Fu Panda, buddy? Mu of f. So let's say this is the average height of. Do you want to come help me teach? Do you want some breakfast? And back to Kung Fu Panda. Okay. The mean of all male heights is 68 inches. I'm just kind of making these numbers up. And let's say the mean of all female heights is 64 inches. And let's say they're coming from two different populations. So this is what our population distribution looks like for each of them. And what we do with these different populations, and when we're taking a difference in means, sometimes our sample sizes are different. So if we take, right here, we took a sample size of n equals 10, and right here, and that should be a lowercase, but the program's weird. And here we took a sample size of n equals 25. What do we notice about the distribution of their means? So what this is like 10,000 or 100, like 50,000 different means. And what I mean by that is we took a sample of 10, calculated the mean, and put it down here. We took a sample of 10, calculated the mean, a different sample, put it down here. So this is the approximate sampling distribution for the means with n equals 10. Over here, we took n equals 25, which means we took a sample of 25, calculated the mean, plotted it on here. So what is mu of x bar m? That is to say, what is the mean of the sampling distribution of all the x bars? Well, it's centered directly on what is above. It is the expected value. So remember, a true sampling distribution would be every possible sample of size 10, you take the mean. So if we were able to look at a population and take every possible sample of size 10, which is, there are too many of them, and then construct a distribution, it would have exactly, okay, it would have exactly the same mean as above. Okay, it would have the mean of this distribution if we were to do that. So this is the approximate sampling distribution, so you can see a tiny little gap right there, but basically it's going to have the same mean. Okay, and so that means over here, if this is the sampling distribution for samples of size 25 for female heights, it's going to have this mean. Same mean as above, even though they look slightly different here, roughly the same. It's important to note that, remember, when we increase the sample size, that's going to tighten up the spread of our sampling distribution. Okay, so up here, we have our spread. This distance right here on our graph, this is sigma m. That is to say, that is the standard deviation of the heights of all adult males. And then over here we have the standard deviation of females. So what the heck is sigma x bar of m? Well, that is the standard deviation of our sampling distribution of the x bars. Okay, so that is this gap. And how do we predict what this gap is? That gap is sigma x bar m. How do we figure out what that is? That is, well, it depends on sigma, and it depends on the sample size. The larger we make the sample size, the shorter that gets. And so what it is it's equal to sigma of m divided by the square root of n sub m. So that is to say, the sample size from the males. In this case, it is 10. Okay, he's back. All right, over here, my little helpy scalper with recording. Sigma of f. Okay, that's this sigma of f, and then you divide by the square root of your sample size. And that was something that we learned back in the day. You can take a look at what we did there. Okay. So that this is going to shrink. This width right here, this tiny width is sigma of x bar f. All right, let's go ahead and scroll on down. I'm going to make this a little bit wider. So let's say, what are we actually doing with the difference of means? So this is the sampling distribution for the means of the males and the means of the females. But this is the sampling distribution of the difference between them. Okay, so where are we expecting this to be centered? Well, based on the rules for adding and subtracting random variables, that should be, and I'm going to switch to green if you guys don't mind. Is that selected? Okay, bingo. That should be at x, so the mean of a difference should be equal to the difference of their means. That is to say, this should be centered, if we are taking and subtracting all of our x bars and our samples, then it should be centered on whatever this is minus that. But we know that they're equal to the centers of the population distribution. So minus x bar f, which is equal to mu of m minus mu of f. So that's crazy, right? So we can take this and we can take two samples, we can subtract them, and it should be centered on the actual distribution means. That's pretty cool. All right, let's go wide. Let's scroll down. Now that this is extra large. So then what the heck is the spread? What is going to be the gap for one standard deviation for this difference? Well, based on the rules that we saw before, that looks like sigma squared of x bar m plus sigma squared, we can add those together, of x bar f. Great. So basically, when we are adding or subtracting random variables, this always stays positive. We can take the square root. So what is this squared? Well, we know up above, let's kind of zoom out a little bit if I can. I don't want to break my computer like I did the last recording attempt. Aha, so the standard deviation of x bar m we know is equal to the standard deviation of m divided by in root, right? Or the root n(m), right? So what we can do here is we can kind of put this in square roots, or in parentheses. We're going to square it, and on the inside we're just going to substitute what's right here, which is the sigma of m divided by root of n(m). And then over here in parentheses we have squared, which is sigma f over the sample size of f. Okay, great. Well, we got squares and square roots, folks. Let's do some simplifying. All right, so that's going to be sigma m squared, all divided by... Hi, Oscar. How are you doing, buddy? What are you playing with? Are you doing some exercising? Okay. Sigma f squared, and then the square root is going to go away here, and f. Okay, or the sample size from the females. And we want to know the standard, so we know this is the variance of this. Okay, but if we want to know the standard deviation, we would take the square root of both sides, and you'd get sigma of x bar m minus x bar f is equal to the square root of sigma squared m over the sample size of the males. So this is the standard deviation of the actual population of males, and the standard deviation of the population of females squared over the sample size of the females. Beautiful. So what does this tell us? Well, now we know with this distribution, we know where it's centered. It's centered on the difference of the means, okay? And how do we know how it's spread? It's spread based on this equation. So that's this standard deviation here. Sweet. So now we've got kind of everything we need to carry forward with doing a confidence interval, except for a couple things, and I'm going to go over those right now. We need to go over the conditions before we do a confidence interval, and these are nothing new. I'm just going to go over them real fast. Data must come from two independent random samples or from two groups in a randomized experiment. So those have to be satisfied for us to continue calculating a confidence interval. When sampling without replacement, we need the sample size to be less than 10% of the population in order to continue with our test. Okay. And then the last one is for each population, we need one of these things to be true. So you need the population to be normal, right? You need the population to be normally distributed, which we don't really know with heights of males and females. They probably are, but we just sampled from class, so we have no information. You need the sample sizes to be bigger than 30. We learned, I don't know if you guys remember when Luke came up and drew in the population distribution, he kind of like spelled out his name or tried to, and then we sampled a really large sample size, and it turned out that the sampling distribution of the means looked normal, right? So that's the central limit theorem. So when this gets, when n gets large, we're good. But if n is less than 30 and we don't know the shape, then we can just check the data that we have and make sure it shows no strong skewness nor outliers. So if we do that, then we're good. All right, so those are the conditions that must be met for us to continue. I think, honestly, these are pretty cut and dry, these two, for the most part, except for spotting outliers and skewness. This one is where it can get a little bit tricky. You just need to make sure things were randomly selected, but you also have, if it doesn't say things were randomly selected, but it mentions a randomized experiment, you're good to go because the treatments have been randomized. And so you should get a representative sample. Okay, so here's the issue. I'm going to need a tissue for this one. So remember, a confidence interval format is a point estimate plus or minus the critical value times the standard error. Now, in a perfect world, our point estimate, what we're using to estimate the difference in population means is just the difference in sample means. That should be understandable. In a perfect world, if we knew the standard deviations of the two populations, then we can use Z down here. But it turns out that similarly to the confidence intervals we did before, since we are trying to guess at the difference in population means, we probably don't know their standard deviations, right? So, what we do is we have to use the sample standard deviations. So we have to come down here and use this in our calculation. And that can be a little tricky. So what are we going to do here? So what we do to compensate for that, since we have two unknowns in our confidence interval, we have to be a little conservative, and we have to kind of spread the interval out a little bit, because otherwise, if we say 95% and we use this and we use sample standard deviations, we're going to end up missing, I guess, we're going to end up missing more than 5% of the time, right? And that's a problem. So we have to use the t-distribution, which is what we did before. All right, so this is the equation that we are going to use for the large majority of our confidence intervals here. Okay, so don't use this one unless you know sigma for the two populations. So you can use Z if you know sigma for both populations, but most of the time we don't know that. I can't think of a realistic scenario in which you would, so this is the one that we use. But there's a problem here, okay? How the heck do we find the degrees of freedom? So remember when you're doing a confidence interval, if we say 95% confident, then we should contain the population parameter 95% of the time. But there's also the chance that, let's say this is our population parameter, there's also the chance that our confidence interval misses high, and there's also the chance that our confidence interval misses low. Okay, so that 5% of error that we have is on either side, which means if we're doing like a 95% confidence interval, we actually take the 0.05, divide it in half, and we're going to use this column. If we were doing, say, a 90% confidence interval, then we would use this column for the error. And the reason is this table is only reading one side of the error. Okay, so we have to kind of divide by 2 and ignore the alpha thing right there. That's just, I grabbed a table that is reading it kind of weird. but it only is only reading to the right. So it's all, when you're using a table, it's all based off how the table is read. Because I think the one out of your book reads in the middle, which can be easy to read as well. Okay. Yeah. So the problem is, though, once we pick our once we pick the column we're in based on our alpha, what do we use for our degrees of freedom? Because before we just used n-1 for our degrees of freedom, but now we have two samples. And so which of the two do we use? Is there a right answer? I don't know. Well, here's the equation for figuring out the degrees of freedom that you're supposed to use. There are two options. Option 1, which I'm pretty sure no one's going to want to use, this is what your calculator does. And I do not expect you to do this by hand. The AP exam does not expect you to do this by hand, but this is a math class. And so that's the equation that is used to calculate the degrees of freedom for this situation. Okay? The other option is called the conservative option, which means our intervals are probably going to be wider than they should be, than they would if we use this option, but it'll work. Okay? And you just use whichever is smaller, the degrees of freedom for population 1 or the degrees of freedom for population 2, or population M and F, whatever one you're talking about. So you just look, you take the sample size from population 1, subtract 1, take the sample size from population 2, subtract 1, and then whichever is smaller, that's the degrees of freedom that you use. So let's go ahead and get started with our confidence interval for the difference of means. So we're going to say that we want to do a 90% confidence interval for mu of m minus mu of f. Okay, so we want to, where, we're going to define what these are, where mu of m is equal to the true mean height, and we're just going to talk about the heights of North Pole High seniors. Okay, the true mean height of all senior boys at NPHS. Okay. We have to do that because we selected from only senior boys at NPHS, and we selected from only senior girls, and mu of f is the true mean height of all senior gals at NPHS. Okay, so let's recap what's in state. We state our confidence level, so we want to do a 90% confidence interval. We state what the confidence interval is for. It is a difference of means. And we state what each of those means are. Bingo. Moving on. Plan. We have to say what kind of interval we plan to do and check the conditions for that interval. So for plan, we are going to use a 2-sample t interval for mu m minus mu f. Okay, so what are the conditions? The ones you're checking are the randomness. I didn't think I made that abundantly clear. The first one in blue was randomness, then we had 10% and the large counts condition. Before, I want you to pause the video here in just a second, and I want you to try and predict, we actually, based on how we collected data, I don't know if you remember this, you guys walked into class, you measured your heights, you measured your wingspan, your limbo height, whatever. We did all that. Some of these, one or more of these conditions is not validated, and I want you to try and take a stab at which ones they are. Okay, and I'm also going to show you the spread of the data. So here's the data. Here's some graphs of the data of the male and female heights, and I want you to tell me which conditions are not validated. You can pause the video there. Pause right now, make your predictions based on what we see, and then we're going to reconvene in just a second. But I'm just going to keep talking. Okay. Randomness. Randomness does not pass. Okay, this is a fail. Okay, we fail the randomness condition check because we did not, in order for it to be truly random from the senior population, we would have had to number all the senior boys, number all the senior girls separately, select a number from each, then record their heights. We did not do that. So the randomness check fails because we didn't take a representative sample from the population, from each population, not all, or rather, I'm just going to say many participants had no chance of being selected. Okay, so on the AP exam, if you got to this point and someone had done a convenience sample and just sampled who was there, that is not representative. You're not taking, you're not giving everyone a chance of being selected, or rather, people are being left out. Okay, so you have some bias inherent in what you're doing, and that's an issue. Okay, so that right there, you'd stop. You're done. Technically, the problem is over, but you know me, we're going to keep rolling. We're going to check everything else, and we're actually still going to do the interval, even though I'm not supposed to. Please forgive me. 10%. Okay, well, let's look at the sample sizes here. Sample size 1, 2, 3. I think this is this is 12. Sample size 12. This is sample size 9 for the girls. Yeah, so this needs to be less than 10% of the population from which we sampled. Well, if you look back here, we see the population of senior boys at NPHS. So in order for this to pass, there would need to be more than 120 boys. And I don't think that there is in PHS. I do not think that there are 120 boys in the senior class, if I had to guess. If there are, this is good. If there aren't, then this is bad. So I don't think that there are. So the 10% condition also fails in this, making that assumption. Okay. This is a fail. It fails because 12 is more than 10% of all senior boys at NPHS. And I don't know about the girls, but you would make that judgment call. So the 10% condition does not work here. Okay, now let's talk about the large counts condition, or test for normal, the test or check for normality. Okay, let's take a look at the data. We got to go through that flow chart. The first thing was, are they normally distributed? Well, we don't know. The next thing is, our sample size bigger than 30? No and no. You don't add them together, right? It's just you look at each one individually, and they're both less than 30, so the answer is no and no, which means we have to go to option 3, as if it's less than 30 and we don't know the distribution, then we look and we check for any outliers, and we check for any skewness, and they look fairly symmetric, I would say. I don't really see too much skewness going on, and I don't these two may look like outliers, but I really don't think that they are if you actually look at the data. Remember, to find an outlier, you check the high end by doing Q3 plus 1.5 times the IQR, the interquartile range, which is Q3 minus Q1. And then you also got to check the bottom to see if that's an outlier, which would be Q1 minus 1.5 times the IQR. So check both of those, and that's the cutoff point for an outlier. So for example, if this dot was less than that number, then it would be an outlier, but I don't think either of these are outliers, so there's no outliers or skewness. It looks like it could be potentially normal, so we'll go back and say large counts condition is a check. There is no apparent, I spell that right? Oh God. There's no apparent skewness nor outliers present in either sample. Of student heights. It is plausible these data came from normal population. I didn't say it did, I said it was plausible that it did, right? Data came from normal populations. Okay, so fail, fail, check. Well, if there's one fail, we can't continue, so that's where you go. Pitch it in the trash. You're done, right? Actually, you can be done right here. But we're going to continue forward. We're going to do the math, assuming that those two actually passed. Poor form. I realize this. Pretend they passed. And we're going to go. We're going for it. So we're going to do this calculation here. Yeah, let's do that. Except this is x bar. We're doing x bar m minus x bar f. So how do you do this quickly? What's the quickest way to do this and show your work? You can do summary statistics inside your calculator to get that value. X bar 1 in this case is 70, or rather x bar m. Yeah, so this is 1. Just remember, let the 1 represent m and 2 represent f. So that's 70 point, I'll say 70.67 minus, for the males, is x bar 1, and the mean of the females is 65.41. Plus or minus, okay, now we got to find our t critical value. We said we were doing a what interval? 90%? Is that what I said? 90%. All right, so let's go to our t-table. Here's our t-table. 90% means we're going to miss 10% of the time. Divide that in 2 for either side. So we're going to be in this column. But what are we going to use for our degrees of freedom? Well, our two options, so we're going to be using this one. Our two options for degrees of freedom are the sample size from the males, -1, and the sample size from the females, -1. Which is smaller? Sample size from the females is smaller at 9, -1 is 8, so we're going to use degrees of freedom 8, and we're going to come down and use 1.86 for that. So our t star value, our t critical value, is 1.86. And we're going to do the square root of the standard deviation of the males squared, or the variance of the males, and that should be, you can do summary statistics in your calculator, and you get 2.578 divided by, that's squared, divided by the n1. N1 is 12. And then over here, we have 2.609 squared divided by 9. And so remember, guys, this is our standard error, right? The standard deviation of our statistic. This is our standard error. This is our t-critical value. This whole thing, the whole term, is the margin of error. And if you do all this math and boil down your margin of error, you should get something close to, and I don't think you're going to get the exact thing here because my calculator used a different degree of freedom. Why don't I just do the math? How about that? Let's just do the math. Golly gee. 2.578 squared divided by 12. Okay. And 2.609 squared divided by 9 is that. So we do this plus that is that number, and then we take the square root of that number. 1.4144 times 1.86. 2.129 is what I got. All right, I'm gonna hop back to my stats here and double check that. 2 sample t interval data, list 1, list 2, confidence level 0.9. I think it's believable. If you use your calculators, you get a much, or not much, but you get a slightly smaller margin of error here if you use the 2 sample t interval or 2 sample t interval, and that is because they are using a different degree of freedom. Remember, they're using that ugly degree of freedom formula, and they actually get a decimal. You'll get a decimal value for degrees of freedom, and I think it ends up being around 17 or something here. Anywho, so I'll take a look in just a sec. But yeah, your margin of error based on these numbers should be 2.129, and we can come and subtract these two things to get our point estimate at 5.26. So let's go ahead and do some math. 5.26. 5.26 plus 2.129. So our upper end is 7.39, and our lower end is, well, you guys can see 5.26, that it's positive, minus 2.129, which is 3.13. Okay, so there's our confidence interval based on using the smaller of 2 for our degrees of freedom. It's a more conservative estimate, which means our interval is going to be a little bit wider, so we may actually capture a little bit higher than 90% of the time, but that's okay. We followed the rules that we were given, and that's what's important. All right, so what does this interval mean for us? This interval means that we are 90% confident that the true difference in difference in mean height between NPHS senior boys and girls is contained in the interval from 3.13 to 7.39. And I think I went off of the formula a little bit there. I think the formula you were given was we were 90% confident that the interval from 3.13 to 7.39 captures the true blah, 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 blah. I think either one of those is fine there. Okay, so how do you do this and check this on your calculator? Well, what does this actually mean? Oh, sorry, this actually means, since we're really 90% confident that that boys are between 3.13 and 7.39 inches taller than girls on average. That's really what it means. So what it means is our boys usually, or our guys, senior boys, usually taller than senior girls. Yes. Now, if you were to do this in middle school, you'd get completely different results. Okay, so the girls in middle school are usually taller than the boys are. But in this case, we're talking about senior boys and girls. 0 is not contained in the interval. Where we would not be able to conclude that boys are taller than girls is if in our interval, if this were a hypothesis test, we would say we have convincing evidence that boys are taller than girls on average, as 0 is not contained in our interval. It's not a plausible value. 0 is not a plausible value in the difference of mean boy and girl height. There you go. So, yeah, that's the way that we interpret that. I'd like to do that for middle school heights. I think it'd be fun. How do we do this on your calculator? There are two options, one of which is better than the other. This is the one that's going to save you a lot of time and give you the answer kind of like straight out. So this is not the data that we use. This is just made up data from your book, but we're using list. You can just use lists. So you type the data for the boys into list 1, you type the data for the girls into list 2, and then it'll give you or vice versa, and then it'll give you your interval. You need to know which one's in boys and which one is girls, and do it appropriately, but make sure the pooled option is selected as no, and your confidence level, don't write it as 90 period, write it as 0.9 for the sake of the test. And then once you've entered this, all you have to do is plug in your data into lists, make sure your frequency is set to 1, press calculate, it'll give you your interval, it'll give you your degrees of freedom. Notice it is a decimal. Oh, sorry, yeah, I don't know what this would actually, does it actually say? Sorry, let me go back. Let me go back to here. I'm going to run that test one more time. Choose sample t interval. Degrees of freedom for this, if you run it in your calculator, is, it's 17.27. Weird. Okay, so they're both similar. So it gives you your degrees of freedom, it gives you your interval, and it spits out your summary statistics all at once. If you do it this way, you have to calculate the summary statistics on your own first, and then write them down, then plug them in, and that to me just seems like a much larger hassle. So I think doing it with lists is a lot easier. Okay, so that's it, guys. Thanks for tuning in and watching this video online. I look forward to moving forward with some of the stuff we're doing in class. We're almost done. We're going to do hypothesis tests for this next, and I'm going to have some sample data that I need you to collect at home. And so I'm going to have a little Google form for you to submit. That is part of your homework for as soon as possible, that we can get that, because I'm going to use that data in the next video lesson. So guys, thank you so much, and hope you're all doing well. We'll see you later.